All right, so let's start this exam, shall we? This is a little bit of a hybrid exam. It's actually got the Lisachem multiple choice, and then if you have a look, it's got all of the neat short answer. But that's fine because there's the same marks for multiple choice and short answer in the exam. In other exams, each exam will have 30 multiple choice. So you'll notice that that's different to our regular 20 multiple choice. But we have 2 hours and 30 minutes to complete it. And your reading time is 15 minutes. Just some things about the exam. I'm sure you all know this by now, but you can only bring in your scientific calculator and you will get a data book provided for you in the exam, and it will look exactly the same as the one that we've given you in class. This is the 2011 one. The only things that's really changed are a couple of the molar masses. Don't know how you can change a molar mass, but anyway, they've rounded it. Okay, so let's just start. Now I'm going to go through all of the questions, but some of them I'll move through quite quickly just because they're more obvious than the other ones and I think more straightforward, but other ones will require greater explanation. So we'll just start with this one, analysis of an organic compound. So we obviously look at lots of organic compounds in chem and we analyze their functional groups through a number of techniques. Infrared's the biggest one for identifying functional groups as well as NMR, but that's more looking at the actual carbon and hydrogen environments. So here we have infrared spectroscopy, and here we have carbon NMR, both of which there are values in your data book. All right. So the way I would approach this question is, first of all, identifying functional groups through the infrared spectrum, because that's probably the easiest one to do. And by now you should notice that something that looks like this, which is not it's a broad peak, it's considered a broad peak compared to, say, the C double bond O, but it's not as broad as the OH of the carboxyl group. So this, to me, is OH of an alk group, alcohol. But a way you can check it is through your data book. And we have here, infrared, OH of alcohol. Does it fall within this range? 3,200 to 3,350. Yes, so it's around here, which is 3,300, sort of thereabouts. Okay, so it's an alcohol group. This is a CH, and a lot of your organics will have a CH. I'm going to say almost all of them. And here we have the fingerprint region, which is sort of due to identifying the molecule as a whole and not really identification of functional groups. Here we might have a CO group, which would be 1,000 to 1,300, so around here would be our CO group. Okay, but anyway, so we have an alcohol. We don't have a carboxylic acid, so the first thing I'd do is have a look at our options, and we have ethanoic acid here, so I would say that's a definite no. Also, if we look at the carbon NMR spectrum, we have two distinct peaks, meaning that we have two carbon environments. So if you have a look, butanol already, two butanol already has 1, 2, 3, 4 carbon environments, so we can automatically cross off butanol. 1 propanol has 3 carbon environments. We don't have 3 peaks, we only have 2, so can't be 1 propanol, which just leaves 2 methylpropantuol. I mean, we can double check it. OH. Alright, so this is 3-methylpropantuol, and we have these 3 carbons all in the same environment, giving us this peak, a 3 peak, the integration is 3 to 1, and we've got our 1 here. Now you can always double check, but you wouldn't have to for this question. This question can be done quite readily, but just to give you a bit of extra help, we were looking for CH2OH around 50 to 90. So that would be here, sorry, it's just here, it's not CH2OH, but it's got a C bonded to an OH. So that would be this one, still within that range. Okay, so that one corresponds to there. And then the other one would be, well, what have we got? We've got it at about 30. So at 30 we can see okay, so if you look at this CH3, which is what we would expect for a methyl group, see how it's a bit above that? Okay, that just means that there is actually more energy required to shift that carbon nuclear spin against the field. And that means that it has less nuclear shielding, and it makes sense compared to a normal methyl group because it's, even though it's not directly bonded to an electronegative element, it's kind of bonded to a carbon which is bonded to an electronegative element, and they've got this sort of rebounding effect on each other. This drags the electrons away, therefore less nuclear shielding for this carbon, and it feels the external magnetic field more, giving it, making it harder to move it against the external magnetic field. So that would be option D. Okay, next one. So this one, you know, a few of you had trouble with it, but let's have a look. Sodium hydrogen carbonate decomposes on heating according to this equation. So this is a chemical reaction. Now the question says decomposition of a 1.275 gram sample, which was moist, of sodium hydrogen carbonate. Moist meaning that this mass, 1.275 grams, is not just sodium carbonate, it's actually sodium carbonate and water. It's like we've got this sodium hydrogen carbonate and we've put it under the tap and it's collected some water. So then this breaks down via an decomposition reaction to produce those products, and we'll get the loss of water via evaporation as well. So they're asking what is the mass of water present in the moist sample. They're not asking for this because that has actually been a product of a decomposition reaction. They're asking for what was this mass. Now, according to the theory of conservation of mass, mass is neither created nor destroyed, so this must break down into this, this, and this, like i.e. these masses joined must equal this mass, okay? And then the rest of it will be H2O. So what I'd do is work out the masses of these, simply add them up, and then do this minus the masses of those. And the way you can do it is through stoichiometry. So the mass of sodium carbonate is 0.528 grams. Okay, and therefore the moles of sodium carbonate is 23 times 2 plus 12. Oops. The moles is 0.0049. That means that the moles of sodium carbonate, H2O, and carbon dioxide is 0.0049. So I can just simply times that by 18, gives me the mass of H2O, which is 0.089, and then I can times that value by 44 to give me the mass of carbon dioxide, which is 0.219, and then I add them together, plus 0.528 gives me 0.836 grams. Okay, 8 grams. So that, option D, is actually the mass of this, or all of these combined, that mass. To get the original mass of the water, I have to do 1.275 minus 0.8386. So 1.275, take away the answer, is 0.438 grams, and that is of the water by itself. So option C. Next one, titration curves. This one's fairly straightforward, so I'm going to move through it quickly. In all the cases, the initial concentration of the acids and bases involved in the titrations were 0.1 m. Okay? So if you want to highlight things in the chem exam, I'd say just highlight the values or underline the values so you remember. Which of the titration curves best applies to the reaction between HCl and NH3? Okay, so ammonia, you guys should know, is a weak base, and HCl is a strong acid. So that's pretty much all you have to know for this equation, for this calculation, because we know that if it's a strong acid and a weak base, the equivalence point will be around 4.5. Okay, so if we compare them all, we have one that's at 7, strong acid, strong base, another one that's at 7, strong acid, strong base, and then we have our answer, which is about 4.5. So it's C. Whoops. A would be a strong base, weak acid. Okay, for example, ethanoic acid and sodium hydroxide. Next question. Which of the indicators listed would be the least suitable choice for any of the 4 titrations? So this question, the main thing is any of the 4 titrations, okay? Not just the one that you're looking at. So what I'd do to answer this question is, I've already done most of it. We've got the equivalence point of them. Remember that the indicator endpoint needs to overlap with the equivalence point. So we have an equivalence point of what, around 8-ish for the one up here. So we need to find something that doesn't overlap with 8, 7, 7, or 4.5. And our options are methyl orange, methyl red, bromothymol blue, and phenolphthalein. So if you look at your indicator chart of your data book, we have methyl orange is 3.1 to 4.4. Then we got methyl orange, methyl red, and bromothymol blue, and phenolphthalein. Phenolphthalein is around 8.3, which would be very suitable for this one. Okay, we've used phenolphthalein with a weak acid, strong base before, and the bromothymol blue one has at around 7, which would be the strong acid, strong bases. And then we have one at 4.5, pretty much between methyl orange and methyl red. And look, we've got one which is almost 4.5, not quite, but one which definitely overlaps 4.5. So methyl red would be suitable for option C, leaving methyl orange as the one that's not suitable for any of the 4 titrations. Alright, so question 4 is A, methyl orange. Alright, so question 5. This one's quite a difficult question, but if we have a look at it, basically we're going to be using our electrochemical series for this. A gas electrode contains a conductive material over which a gas is bubbled or collected. Remember what the gas electrode looks like. We have that sort of funny looking thing where the gas goes in, and we've got sort of a carbon inert electrode. and then we have our solution in here. So we need basically something that's going to be a gas, because it says a galvanic cell was constructed which contains 2 gas electrodes, so we need something with gas in it. The operating cell voltage is 1.22 volts. Which of the following observations made is most likely to be accurate? Okay, so let's have a look. I would just mark it on your data book in pencil so you can rub it out. But anyway, so the gas ones, we've got fluorine, chlorine, oxygen, oxygen here, oxygen again, hydrogen gas, yeah, and then pretty much goes into metals except for down here. Okay, so we need something with a difference of 1.22 volts. Now, you could just simply go, 0.83 to 0 is 0.83 volts. We need something with 1.22. It's pretty much trial and error. If you're good at maths, you'd be really quick at this question. And then you have a look and you get something like 1.23 to 0. That gives us a 1.23 volt, and we might be persuaded to think it's actually this one and the hydrogen. Okay, so that's the one I thought it was first. If you just have a look at the options, a solid is produced at the anode. So in other words, because it's saying that it's a gas electrode and it's a galvanic cell, then the spontaneous reaction would be this one, okay, and then beyond that, and the solid's not produced at any of them. So you can look at the next one. Gas is produced at the cathode, okay, and then you have a look, and we have reduction at the cathode producing a liquid, so it can't be that. pH increases at the anode, so this way we have the reduction of H plus, and we have and we might be persuaded to think that it's this one, but then if you look, you actually have one which is closer, which is H2S and chlorine. H2S and chlorine. Okay, so let's have a look at the options for that. Alright, so because it's a galvanic cell, the spontaneous reaction will be this one going this way and this one going in the reverse. Okay, and if you have a look at the options, so this would be at the anode and this would be at the cathode. Oops. And then you have a look at the options and it's got a solid is produced at the anode, and bingo, we've got solid sulfur being produced at the anode. The gas is produced at the cathode. No, something aqueous is. pH increases at the anode. No, pH decreases at the anode. pH increases at the cathode. No, there's nothing to do with pH here. But the other thing you can think about, and make sure you don't get confused with this, just because at the anode pH decreases doesn't mean at the cathode pH increases. Okay? Alright, next one, very obvious. Not even going to go through this really. Which one's the least likely to be produced when perchloric acid acts as an oxidant? Okay, so we've got this. We have a look at the oxidation numbers, +1 and +7. Okay, and we have a look for where chlorine does not change or oxygen doesn't change, and it's here. It's still -2 +7. So that was actually, if that would be produced, it wouldn't be the product of a redox reaction. Okay, next one. This one's quite fun as well. This reaction is most likely described as, now you have a look, what's changing to determine if it's a redox reaction, we need to use the oxidation number rules. And if you have a look, we've got -1 here, +1 here, because metals in group 1, like magnesium, sorry, that's group 2, but group 1 and group 2 take priority, so these would both be the charge of their valency, +1 and +2, giving hydrogen a -1. So that was one of the exceptions. Hydrogen's usually +1. Well, it's +1 when with non-metals, but when it's present as a metal hydride, it's -1. Okay, and then we have -2 for oxygen, +1, non-metals, and got +1 for lithium. Lithium doesn't change, but hydrogen goes from -1 to 0 and +1 to 0, so it's both oxidized and reduced, but in different starting forms. So it's definitely a redox. Now the second thing is it an acid base? Because we need to, determine if it is. If you have a look at it, definitely what is an acid base reaction? Okay, if we have an OH negative here, that tells me that water has donated a H plus, so H2O donated H plus and acted as an acid. Okay, and the lithium hydride has accepted, the H has accepted the H plus to become H2 gas. So the lithium hydride has acted as a base. So it's both a redox and acid base. Okay, over here. Now, 1.5 grams of glucose in XX oxygen was completely oxidized. The calibration factor was 2.35 kilojoules per degree Celsius. That should really have that per there. The temperature before, so initial temperature is 22.7 degrees Celsius. Need to determine the highest possible temperature. So we're basically going to determine delta T and then add that onto the initial temperature. So we have the calibration factor, but we also have if I get my data book, did I leave that up here? On the last page you have the specific heats of combustion, molar enthalpies of combustion. You have one for glucose, so that's -2816. So 1 mole of glucose releases 2816 kilojoules. Okay, we've basically got to find energy, okay, in kilojoules. So how many moles do we have? Not one. We have 1.05 divided by 180. That's the molar mass of glucose. Releases X kilojoules. Now if you just solve for X, you will get 1.05 divided by 180 divided by 1, you can do that, 2816, 16.43 kilojoules. Okay, so if you get that, then you know, well, there are two things. We know that energy equals calibration factor times delta T. Okay, so if you want to use that equation, so we are trying to work out delta T, so move calibration factor to the bottom. So energy divided by delta T, which would be divided by calibration factor, which would be this divided by 2.35. So our delta T is 6.99 degrees Celsius. Now to get our final temperature, we have to do delta T, oops, not delta H, plus T initial, 22.7 plus 6.99 gives us 29.7, so that should be B. Alright, so question 9. It looks a little confusing, lots of information. So a redox battery is a rechargeable battery that exploits the ability of vanadium in 4 different oxidation states. The species which can exist in solution appear in the standard high potentials below. Okay, so let's have a look at what the question's asking us. The half equation for the reaction occurring at the positive electrode when recharging. So what occurs at the positive electrode when recharging? We have the anode at the positive, so we have oxidation. So we have electrons on the left. Okay, on the right. So if you have a look at all of these, we can automatically cross off the reduction reactions, which there are 2, and we have 2 possible oxidation reactions. So let's have a look what our species could be. When the battery is delivering energy, the electrolyte at 1 contains +5 and +4 oxidation states, and at the other contains +3 and +2 oxidation states. So if you have a look at them, we have this, basically pick the ones that have either +5 and +4, the redox pairs, or +3 and +2. So if you have a look, we have -2 here, and then it has to equal +2, so we have +5. Okay, +5 here, and we have -2 here, making it -6. -6 overall equals -1 plus, +4 here. +4 here and a +5 here. Okay, so it's most likely this one. Let's just make sure we can rule this one out. We have a +3, and if this one's a +2, we'd have to do further investigation. But lucky for us, we worked it out before as a +4. So there's no redox pairs according to the equation, to the information that differ in a +3 to +4. So it has to be option A. All right, next one. Try and rub it all out. Okay, so if you have a look at this question, and it is a Le Chatelier's question. Okay, we've got the data shown in the table below. Investigation. All right, so we're investigating a couple of factors: temperature, pressure, on yield, their effect on yield. On the basis of this information, so what do we notice? As temperature increases, so we compare 200 to 300, but we'll keep pressure the same, because we don't want, when you're comparing factors, you need that to be the only thing that changes between the experiment, and everything else kept constant to actually accurately compare. Because if we compared this 200 to this, we might think it's temperature increasing, but we're also changing pressure. So we compare these two for temperature. So as temperature increases, what is happening to the yield? It is decreasing. Yield decreases. Okay, now for pressure, we've got to keep it where the pressure changes, but the temperature stays the same. So these two, as pressure increases, yield increases. Okay, so according to Le Chatelier's, as temperature increases, the system will want to partially oppose the change by decreasing temperature by favoring energy absorbing endothermic reaction. If this was an endothermic reaction, the forward reaction, there that would mean that yield would increase as temperature increases. But because they have this inverse relationship, we know that it is an exothermic reaction favored by low temperatures, not high temperatures. So we know it's exothermic, therefore it can't be A or B. Now, as pressure increases, yield increases. According to Le Chatelier's, as pressure increases, the system will want to decrease pressure, and it does this by moving or by favoring the side with least number of particles. Because yield's increasing, that means our products have the least number of particles. Therefore, fewer particles on the right-hand side. So it has to be D. Okay, question 11. Which of the following statements about fuel cells is most accurate? Okay, if you have a look, we've got fuel cells only convert chemical energy to electrical energy. They do convert chemical energy to electrical energy, but this would be saying that it's 100% efficient, which it is not. Okay, 100% efficient, therefore it's actually producing heat energy as well. Fuel cells utilize only acid electrolytes. No, we did the basic fuel cell. Fuel cells are rechargeable. No. Fuel cells indirectly involve combustion reactions. Okay, the thing with this is it is indirect combustion. Okay, we do have a fuel going in on the right and on the left. We say H2 and O2, and we get the product of H2O. That is a combustion reaction, and it can occur, well, let's see if it will occur spontaneously. It has to, because it's not an electrolytic cell. Let's say we've got the acid electrolyte, we would have this one and this one. Occurs spontaneously. If we allow them to just react spontaneously, we will not get electrical energy at all. It won't be a fuel cell, it'll be a direct combustion reaction. Okay. If you don't believe me that H2 is combustible, we have the heat of combustion for H2. So it is this option. But you could have done that by eliminating the other ones. So I guess commit that to memory. Fuel cells indirectly involve combustion reactions. We can have a methanol fuel cell, which we've done an example on before, and we've got that direct combustion. But in a fuel cell, we introduce the O2 to one side, CH4 to the other side, and we get this indirect combustion. We want it to be indirect because we will get the flow of electrons from one to the other. And in this case, oxygen will oxidize this, so it will be reduced and the electrons will move towards the oxygen. Okay, next example. This one's fairly straightforward. Okay, for students investigating the stoichiometry of the reaction between aqueous, blah, 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 blah. So we're looking at a reaction between barium chloride and sodium sulfate. Okay, we will get, it's a double displacement, we will get barium sulfate, which is a precipitate, and sodium chloride. Two of those to balance, and we are balanced. Okay. Now, they're looking at the mass of barium sulfate formed versus the volume of barium chloride added, and they're keeping the moles of sodium sulfate the same. So the moles of sodium sulfate, oh, we don't need to do that, equals 0.34 times 0.1, 0.034 moles. Now, the first thing you'd have to do is find out how much barium sulfate you can possibly produce. This one is saying that basically this one's always in excess, and we're adding barium chloride. Doesn't matter how much we add, we get lots of product. So I'm thinking that that's most likely incorrect. Thinking maybe between these two. But anyway, if you have a look, the moles of barium sulfate, the moles of sodium sulfate is 0.034. That means the moles of barium sulfate is 0.034. And the mass of barium sulfate would be 137.3 plus 32 plus 16 by 4, 7.9 grams. So that's just diastoic. Okay, and if you have a look, we have one at about 8 grams here, one at about 8 grams here. The other ones have to be wrong. Okay, so then we look at the next thing. How much barium chloride would we have to add? Well, in this example, we are doing 0.5 molar barium chloride. So the moles of barium chloride are equal to the moles of sodium sulfate, which equals 0.034 mole. The volume of barium chloride equals N over C. Remember, N equals CV. Okay, equals 0.034 divided by 0.5 equals 0.07. 0.068. So that is 68 milliliters. Okay, and if you have a look, we've got one where we require, I don't know, about 34 milliliters, and then the other one, which is a clear 68, so it would have to be graph D. Okay, and then if you look at the other one, which of them describes with 1 molar barium chloride? So we double the concentration, so we halve the volume that we need to have, which would give us that graph 1 option. Okay, next one, a little bit of atomic absorption. Why not? The nickel content of a sample is identified by atomic absorption, blah, 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 blah. Their absorbencies are measured and a calibration curve is plotted. Okay, so let's have a look. 5 grams of the ore, 5 grams was added to 200 mil HCl, and to extract all the nickel aqueous ions. 225 mil aliquots were then taken and their absorbencies measured. The average absorbance was 0.66, so you just start off by going to 0.66, which would be, this would be 0.65. So around, what have we got? 140 milligrams per liter. Alright, so we've got 140 milligrams per liter. Basically, that's in the 25 mil aliquot, but also in the 200 mil original sample, because remember, the concentration, if you take an aliquot, the concentration remains the same. So we take an aliquot, basically the concentration is 140 milligrams per liter in here. We don't have a liter, we have 1/5 of a liter, so you would do 140 divided by 5 is 28 milligrams in 200 mils. All of those grams must have come from the original 5 grams. So in this 5 grams we have 28 milligrams. Now to work out the percentage by mass, we would have to change the milligrams into grams, which would be 0.028 grams. and then we would just simply do percentage by mass, 0.028 divided by 5 times 100. .56%. Closest one is B. Well, to one significant figure is B. Alright, next one is very tedious. The mass in picograms of carbon atoms in one molecule of 2-methyl butanoic acid is what? Alright, so the way I'd approach this, I would first of all work out how many carbon atoms there are in one molecule of butanoic acid. And I'll go, okay, 2-methyl, methyl has 1 carbon atom, butanoic acid 4 gives us a total of 5 carbon atoms, and 5 times 12 is 60. Okay, so therefore there are 60 grams per mole. In other words, the molar mass of carbon is 60 grams per mole in that per mole of this compound. So if you have a look of this molecule, so if you have a look, I just do a ratio. There are 60 grams of carbon in 1 mole of molecule, and then there are X grams in 1 molecule. Now they have to be in the same units. This one's in moles, this one's in molecules. I'll put that in molecules, which would be Avogadro's number, 6.02 times 10 to the power of 23. Okay, so simply solving for X, 6.02 times 10 to the power of 23, 1 divided by that, times 60. So we have 9.96 times 10 to the power of 23 grams. Now we have to go to picograms. Now what I'd use is the data book. So you can just do one quick conversion. Okay, and the way you can remember it, we've got this little thing, but also picograms, 10 to the negative 12. Okay, do we expect to have more picograms or less? And the answer is more. So instead, I wouldn't have to times it by 10 to the negative 12 because that'll make it a lower number. I would have to divide it by 10 to the power of negative 12, which would be 9.97 times 10 to the negative 11, which would give us B. Okay, question 16. When potassium permanganate was used as an oxidizing agent in a galvanic cell, it produced 2,290 coulombs of energy, and 1.5 grams of it was consumed in the cell. Assuming the conversion is 100%, what is the product of the reduction of MnO4? Negative. Okay, so we're given Q here, we're given a mass, we can work out the moles. Okay, basically we're going to have to find out how many electrons it's used as an oxidizing agent, so it's being reduced. So how many electrons it would have to gain. Okay, so if you have a look, we've got Q equals NE times F. The moles of electrons equals Q divided by F, 2290 divided by 96500. So the moles of electrons is 0.0237. Okay, that means to make this many moles of, to use, this many moles of KMnO4, it actually required to consume that many moles of electrons. So that will be the mole ratio. So we've got to find out the moles of KMnO4 is mass over mole mass, 1.25 over, what's the mole mass? 54.9. So 40.1, oh no, 39.1 plus 54.9, 16 times 4. 1.25 is 0.0079 mole. It makes sense that we require to consume more electrons. You'll never have to consume less electrons than you need to consume of your actual oxidant, because it will always be plus. You can't add half an electron, half a mole of electrons. Okay, so we have this ratio. The moles of electrons is 0.02737. The moles of Mn, blah blah blah, is 0.079. So we just do an empirical formula type of thing. We do 0.0237 divided by, so it's 3. So we get 3 electrons to 1 KMnO4, meaning NO4 negative plus 3 electrons would produce our product. So we need something that goes down in oxidation number by 3. So we have 2 negative and plus 2. What do we start off at? Negative 2 makes it negative 8 plus 7. So we start off at plus 7, so we need something at a plus 4. This is negative 2, so that's negative 6 plus 3. This is negative 2, so negative 4 plus 4. C. Because if you look at the other one, negative 2 plus 2, and that's negative 8 plus 2, so it's plus 6. So it needs to be C. Okay, so next one. The next one's fairly straightforward. Let's have a look. Okay, so this particular carboxylic acid reacts with the compound X, and we get a salt of sodium, and not ethanoate, but it would be acetyl salicylate. Okay. So what needs to react with our carboxylic acid? Well, we would need something with sodium in it, and all of these options have sodium in it, so they don't really help us. But let's have a look at what else is produced. Carbon dioxide and water. So we know that if we react an acid with a hydroxide, we will only get a salt and a water, so we can't do that. Carbonate, we will get carbon dioxide. Chloride, no. So it's either sodium carbonate or sodium hydrogen carbonate. So I'm just going to write it like that. Sodium carbonate produces CH3COONA plus H2O plus CO2 and CH3COOH plus sodium hydrogen carbonate produces we get the same products, but the mole ratio, we're looking for a 1-to-1 mole ratio. And let's balance 2 of these. 2 of these, is that balanced? Yes. Carbonate, yep. And here, that's already balanced, so this is a 1-to-1 ratio, therefore we needed sodium hydrogen carbonate. Alright, next one. We have a nice little polymer made up of many monomers. I wouldn't even read that. Equal number of both monomers. Great. Thanks for telling us that. Alright, so let's have a look. Basically, the monomers are lactic acid and glycolic acid. So they both need COOH groups because they're both acids. Okay, so is there an example where this one doesn't have COOH, so it can't be that. And it can't be that. Alright, so it needs to be either of these. And let's have a look at our polymer, which had to have been produced because we've got ester groups, by condensation, polymerization. Okay, so if you have a look, let's have a look. Well, basically water would have come out of every point at which there is an ester group. So we have C double bond O OH. This is how I'd finish it off, and here there'd be an OH here, making this one of our monomers, CH2 COOH OH. So that's a possibility. That's a possibility. Okay. Now the other one, we've got COOH H2OH, yep, so definitely it's that monomer. But have a look at this side. We've got CH3, C double bond O, OH. So we'd have a carboxyl group on one side, and on the other side we'll have an alcohol, hydroxyl group. So we'd have something that looks like OH on one side, CH, CH3, COOH, giving us option A. It doesn't have two carboxyl groups. It's got one alcohol and one carboxyl group. Okay, question 19. Alright, the impact of a change imposed at time t is shown on the rate versus time graph below. So the change imposed on Simpson was, so when I look at time t, okay, first of all we have a dotted line here and we have a straight line, so therefore we have rate of forward and reverse reactions. So if you, we don't know which one's which though, but that's okay. Let's have a look. They're at equilibrium here, then we impose a change at time t, and it must have been a sudden change to the system. Now, if we added NO2, let's have a look at that option. That would increase the rate of only one reaction straight away. It would increase the rate of the forward reaction. The rate of the reverse reaction, so instantaneously at time t, it just shows you that concentration shoots up. Same with the addition of N2O4. So basically, because the rates of the forward and the reverse reaction instantaneously increase, it can only happen if the concentration of both increase. Alright, so if you have a look, increase the container volume. If we increase the volume, we actually decrease concentration. So therefore the rates would decrease according to the rate theory. So therefore it has to be D, which is decrease the container volume. Okay, next one. Basically 0.1 M solution of a weak acid plus H2O produces W negative, weak acid plus H3O plus. Okay, a 10 mil aliquot of that weak acid is diluted to 250 ml with water, the pH of the diluted solution would be expected to be what? Alright, so let's have a look. Basically, there are two ways that we can do this. We can use Ka or we can use logic. Alright, let us use logic. So, if we're diluting something, we'll use the formula C1V1 equals C2V2. Okay, and so we start off with a concentration of 10 to the negative 2.6 because our pH is 2.6 times, oh, by the way, we are using the concentration of H plus because we're looking at pH. We're not using this concentration because it doesn't tell us anything about pH because it's a weak acid. So the initial volume is 10 mils equals C2 final concentration times final volume. So 10 to the power of negative 2.6 times 10 divided by 250 equals 0.0001 molarity. So instantaneously it'll reach that molarity. Now if we do negative log of that, 3.99. Alright, so we might be persuaded to think it's D, but if you think about it, it's a weak acid, therefore it's in equilibrium. According to Le Chatelier's, if there's a change opposed to the system, so here we have a dilution happening, okay, what it wants to do, because there is one particle on this side and two on this side, remember you don't really include water because water is just in any aqueous solution, so one here and two here. We are diluting, so the system will want to move to the side with the most number of particles to increase the concentration of H3O+. So it does this, but it never gets it to the original, which would be 2.6, and it would never get it lower, but it would get it something, you know, in between. Okay? Another way you can do it is through Ka. Okay? We have basically W negative Ka equals W negative times H3O plus over concentration of our acid at equilibrium. Now, the assumption we make is that it doesn't dissociate much, so the concentration of our acid at equilibrium is equal to the initial concentration, which is 0.1. The other assumption we make is that water doesn't ionize to any significant extent, meaning that the concentration of W negative and H3O plus will be equal. So in other words, it will be 10 to the negative 2.6 squared. 10 to the power of negative 2.6 squared divided by 0.1 gives us a Ka equals 6.3 times 10 to the negative 5. Alright, now we can use this information because we know that we've diluted it. C1V1 equals C2V2. Concentration of the acid initially times the volume equals C2 times 250 equals 0.004 molar. Alright, so if we look at that, we can simply determine the concentration of our H3O plus through using the Ka that we derived times 6.3 times 10 to the power of -5, and then we get the square root of that. We will get 0.0005 molar. You get the negative log of that equals 3.3 pH, which is option B. Okay, so that's sort of the way you would do it if given it as a short answer question. Alright, next question. In a gas-fired power station, some of the energy available from the combustion of methane is used to convert water in a boiler from liquid water to steam according to this equation. If the transfer of energy from the combustion to water is 40% efficient, what mass of methane would be consumed in producing 1,000 kilos of steam from liquid water? Now this one's quite straightforward actually. This one's fairly beaker level. Okay, so we've got basically the heat of combustion equals 44 kilojoules per mole. That means if we have 1 mole of water, we require that many kilojoules to convert it from liquid to steam. How many moles of water we have? We've got 1,000 grams divided by the molar mass of water gives us X kilojoules. If we know that for 1 mole, 44 kilojoules, so basically timesing the mole by the delta H. 1,000 over 18 times 44 equals 444.4 kilojoules. So energy we need is 424.4 kilojoules. We have to basically find out how much methane we require to burn to get that many kilojoules. So we can simply grab our data book, got the last page, methane 889 per mole. So 1 mole releases 889 kilojoules. X mole releases 2444.4 kilojoules. So we divide that by 889. Yep, 2.75 kilojoule, 2.75 mole. How many grams? So mass of CH4 moles times molar mass. 2.749.6, so 2.75 times 1216, and that should be 33.9 grams, giving us option B. Oh, hang on. Gosh. This tells you to read the question. 40% efficient. Okay. So we kind of have to look back at this. Now at this point, if I saw that now, I would just say, oh, we require a lot more. How much more? We would require 44 grams if it was 100% efficient, X grams if it was only 40% efficient. $44 grams at 40% over 100, so times gives us 110. I would just do it like that, but that might not make sense to some of you. So you could have just gone, okay, so the energy required is 244.4 kilojoules. Now we know, according to this, the data book, that methane, 1 mole, releases 889 kilojoules. 889 kilojoules, but that's if it's 100% efficiency. So if it's only at 40% efficiency, we just do 889 times 0.4. So 1 mole actually gives us only 355.6 kilojoules. X mole gives us 244.4 kilojoules. Sulfur X equals 6.87 mole. Mass is moles times molar mass equals 109.98, 110 grams, giving us option C still. Okay, question 22, filling in the blanks. Now, if we have a look, the passage below which appeared in a brochure for food analysis, okay, for food scientists, something is a powerful tool for product composition and testing, okay, so looking at things in food, the composition of things in food, and we know food is a massive mixture, so I would already be crossing out A and B. So something like chromatography would be much more useful. And considering the nature of the major components in food, so there's lots of organic compounds in food, okay, and gas chromatography can't be used because food cannot be, turned into a gas. So it would have to be HPLC, giving us D as the answers. So, I mean, in food we've got mostly protein, carbs, fats. So they're kind of analyzed using chromatography. They're large molecules and they will decompose if heated in gas chromatography, for example. Alright, so question 23. The titration. Okay, in an analysis to determine the concentration of HCl in brick cleaner, 10 mils of brick cleaner was diluted to 250 mils with water, and 20 mil aliquots and 20 mil aliquots so the volume of Na2CO3 is 20 mils, so it's the aliquot. The titration of the reaction is blah blah blah. Which of the following equipment rinsing techniques would result in a lower than a true calculation in the concentration? Okay, so we've got our brick cleaner, HCl in there, and we have our Na2CO3. So if we rinse the pipette with water, that will dilute Na2CO3, making meaning that there's less HCl required. So option A, less HCl required. So we perceive as more concentrated. B, rinsing the titration flask with the diluted brick cleaner. Titration flask with the diluted brick cleaner, that's fine. Water in the titration flask before the acid is added, so we will dilute HCl, more required. Thinks lower concentration. Rinsing the burette, the titration flask, sorry. titration flask, we are actually diluting it with 250 mils of H2O, actually 240 mils of H2O and 10 mil of brick cleaner. So if we rinse it, that's the volumetric flask, the titration flask, it doesn't really matter. But D, definitely rinsing the burette with water means that we decrease the concentration of HCl, meaning that we will perceive it as a lower concentration compared to what it actually is, therefore giving us option D. Okay, mass spec. The mass spectrum of organic compound is shown below. The infrared spectrum shows you a narrow absorption peak at C double bond O. The carbon NMR spectrum shows 3 signals. Okay, and a quartet at 4.1. Oh, we've done this one before, so I'm just going to simply circle it. This one's just a really obvious one, and it was A, ethyl methanoate. Consider the 2 semi-structural formulae of the alcohols below. The following, the 2 compounds represented would not have different reactions with acidified dichromate. So you remember that when it is would not have different, so we're looking for something that's the same basically. Okay, so let's have a look at acidified dichromate. Basically you remember that it is oxidized by acidified dichromate to convert COH into C double bond O. Okay, so remember that there are 2 possible products. If we have it at the end, if the OH is at the end, we will get C double OH. So we'll get a carboxylic acid. Okay, and if it's in the middle, we just get a ketone group. Okay, so here we've got it in the middle. Okay, so we would only get, this would turn into a ketone group, and this would actually become a carboxylic acid. So it can't be A because we want them to have the same product. The mass to charge ratios for the parent ions on their mass spectra, simply adding up the molar masses. So we've got 1, 2, 3, 4, 5, 6. 12 times 6 plus 3, 6, 9, 12, 14 plus 1 oxygen equals 102. Other one, 12 times 1, 2, 3, 4, 5, 6. Yeah, plus 16 plus 3, 6, 7, and yeah, is 102. So they would have the same, so it can't be B. Infrared spectra below would not have different infrared spectra below. Sorry, we're looking for something that is. Yeah, sorry. Oh, so it can be B. It has to be B because they would have the exact same mass to charge ratio. Okay, let's just cross out the other ones. So C, infrared spectra below the fingerprint region, definitely different. Number of peaks on carbon NMR spectrum. So let's have to see how many peaks this would have. 1, 2, 3, 4, 5, 6. And this one would actually have, wait, does it have any symmetry? Oh no, 1, 2, 3, 4, 5. And this one would have 1, 2, 3, 5. This one would have. So this one would have 1, 2, 3, 4, 5. That would be 1. And this one would have 1, 2, 3, and 4. 4 versus 5. Okay, nearly there. Alright, the concentration ion graph shows the impact of 50 mils of water being added to 50 mils of an. So we have 50 mils of 0.1 m aqueous solution. So we are diluting. So therefore we're decreasing the concentration of OH negative. So to decrease the concentration of OH negative, let's have a look at all of these examples. HCl plus H2O produces H3O plus Cl negative. Well, we should know that that's a complete reaction. So therefore, at time t, let's have a look at what's happening. We're decreasing the concentration of OH negative. And how is the system responding over time? It's aiming to increase the concentration of OH negative. So it needs to be something weak. So it wouldn't be this. NaCl would be totally wrong because we just have Na plus and Cl negative. Okay, it wouldn't really change the concentration of OH negative, only with water. And the other two are CH3COOH and NH4 plus. Okay, so if we have a look at NH3, it's an equilibrium reaction because ammonia is a weak base. We get H2O plus and OH negative as our products. We get NH4 plus and OH negative as our products. Okay, so if we have a look, because this is an equilibrium reaction, if we dilute it, we decrease the concentration of OH negative. In other words, we're decreasing the concentration of the particles in solution. So it wants to increase the concentration, and it does this by moving to the side with more particles. So the right, increasing the concentration of OH negative. Okay. Now, if it was this other one, CH3COOH plus H2O produces H3O plus CH3COO negative. If we are actually diluting it, the system will want to move to the side with more particles. Remember, we don't include water because it's just present in all aqueous solutions. So we have 2 particles on this side, 1 on this side. So if we decrease the concentration of particles in solution, it will want to increase, favoring a forward reaction. And that would actually increase the concentration of H2O plus, further decreasing the concentration of OH negative. But because we get an increase in OH negative, it has to be C. Alright, which one of the following statements best distinguishes fuel cells from electrolytic cells? Okay, the supply of reactants is from the outside of the cell. Okay, so that's not true. Fuel cells, we have best distinguishes. It is true. So best distinguishes. Okay, so we need to find something that pretty much is the distinguishing feature between fuel cells and electrolytic cells. And that to me would be its energy conversion. So we'll just see if there's one with an energy conversion. the conversion of chemical energy to electrical energy. Fuel cells definitely convert chemical to electrical, whereas electrolytic convert electrical to chemical, so it needs to be there. If you have a look at the other ones, the use of aqueous electrolytes, both of them can use it. You can have molten as well in electrolytic. The movement of electrons away from the anode, they move in both cases from the anode to the cathode. That makes sense. The supply of reactants from outside the cell. Well, this also does happen in a fuel cell, but it happens in some electrolytic cells as well, so it's not the best distinguishing features. Okay, so it has to be option B. So last page, question 28. A current of 2.5 amps is passed for 50 minutes. So this is time, this is I, through two connecting cells in series as indicated on the diagram below. These cells contain molten potassium iodide and silver nitrate. So in the silver nitrate we have as possible oxidants and reductants on this side. As possible oxidants we've got Ag+. Let's just consult our electrochemical series. Where's Ag+? Over here, Ag+, and we have water, but automatically Ag+ wins. And as possible reductants, we have H2O, which is the only one. And in the other one, we only have potassium and iodide. So iodide is the, let's have a look where it is the reductant. And this one's the oxidant, K+. Which of the following substances would be likely to be produced during the electrolysis? Okay, so let's have a look. Now, hydrogen. Is hydrogen going to be produced? H2O is the reductant. Okay, so as you can see, this is the reaction where H2O is the reductant. We don't get any hydrogen gas, we do get H+. Silver, pure silver. So it has to be A. Forgot that we were actually finding what is the least likely. Okay, but silver will be produced, iodine will be, and potassium will be, because we'll get iodine going this way, potassium going that way, being reduced, water going this way, and silver going that way. So that one was fairly straightforward. Okay, 29. 50 mils of 0.1 molar HCl is added to 50 mils of potassium hydroxide, and the reaction is allowed to proceed to completion. The concentration of potassium ions in the resulting solution is potassium hydroxide and HCl, producing H2O plus HCl. Now this is in the aqueous form, so is this, and it completely dissociates in water. Same with this and same with this. So if you have a look, K+ is involved in although it's, it's actually included in the acid-base reaction, it's actually a spectator, meaning that its concentration will not change from start to finish. It exists as K+ initially and finally. So therefore, the only thing we're doing is diluting it. We have the moles of K+ equals CV, 0.3 times 0.15 times 0.5 equals 0.015. So that's the moles. Now all we're doing is changing the volume. The volume of K that K+ is in is 50 plus 50 is 100 milliliters. So in other words, it's 0.015 divided by 0.1 equals 0.15 m, giving us option B. Alright, now Can we focus this? Alright, next one. When 50 mils of nitric acid is added to 50 mils of potassium hydroxide, the temperature of the mixture increases by 6.4 degrees Celsius. What would be the temperature change when 25 mils of each solution are mixed together? Okay, so basically we're saying that they are reacting at the correct mole ratios. You get an increase of 6.4 degrees Celsius. Now, when they when they're at the same concentration, but we add half the volume, we would actually expect half the energy change. But because we are heating half the volume of water, we get the same temp change. So we will expect 6.4.